Hello everyone, welcome to my channel Way to Save Success. Please subscribe my channel and press the bell icon to keep update. Share the link to help your friends. Today we learn about the different topics of light chapter. It is the part 4 and the next part of the light chapter. In the part 4, we learn about the refraction of light, laws of refractions of light, refractive index, spherical lens, and different numerical problem on spherical lens, refraction through spherical lens. Refraction of light. When light travels obliquely from one transparent medium to another, it gets bent. This bending of light is called the refraction of light. So, when light travels from a rarer medium to a denser medium, it bends towards the normal, and when the light travels from denser medium to a rarer medium, it bends away from the normal. In the first diagram, light is passing from rarer medium to a denser medium. So according to the rules, light will move towards the normal. In the second diagram, light is passing from denser to a rarer medium, and according to the rules, light is passing far away from the normal. For an example, when a ray of light passes through a rectangular glass slab, it gets bent twice at the air-glass interface and the glass-air interface. In the given diagram, light is passing from air to the glass in the first medium, and after refraction through the glass, again it incident on the glass-air interface, and again refraction takes place, and the emergent ray from the glass slab is parallel to the incident ray and is displaced through a distance. Here, angle of incidence and angle of emergence will be equal, but not that angle of incidence and angle of refraction. Laws of refraction of light. There are two laws of refraction. First laws, the incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. Second point, the ratio of the sine of angle of incidence to the sine of angle of refraction is constant for a light of given color and for the given pair of media. The second law is known as the Snell's law of refraction. According to this law, sin I by sin R is equals to constant, where I is the angle of incidence and R is the angle of refraction. The mathematical expression got from Snell's law is sin I by sin R equals to constant. This constant term equals to the refractive index. The absolute refractive index of a medium is the ratio of the speed of light in air or vacuum to the speed of light in medium. The relative refractive index of a medium 2 with respect to medium 1 is the ratio of the speed of light in medium 1 to the speed of light in medium 2. This definition is applicable when two different medium are present and light is passing from medium 1 to medium 2. Condition for no refraction. Refraction will not take place under the following two conditions. First one, when light is incident normally on a boundary. A ray of light traveling in medium 1 falls normally. Therefore, angle of incidence I equals to 0 according to Snell's law. Sin I by sin R equals to N2 by N1 or sin R equals to N1 by N2 into sin I. Therefore, that is equals to N1 by N2 sin 0 degree. And the value of sin 0 degree is 0. Hence, R value is coming 0. Thus, there is no deviation in the ray at the boundary. Hence, no refraction occurs when light is incident normally on a boundary of two media. Second point, when the refractive index of two media are equal. When the refractive index of a media 1 is equal to the refractive index of the medium 2, then N1 equals to N2. Then according to Snell's law, sin I by sin R equals to N2 by N1 equals to 1. Therefore, sin I equals to sin R or I equals to R. Hence, no refraction occurs at the boundary that separates two media of equal refractive index. Everyone knows about the spherical lenses. In the spectacles, the lens which we are using, that is also a spherical lens. So, a spherical lens is a transparent material bounded by two surfaces, one or both of which are spherical. Spherical lenses are of two main types. They are convex and concave lenses. Convex lens is thicker in the middle and thinner at the edges. In the diagram given here is a convex lens where the middle portion is thicker and the edge portion is thinner. Now, when the ray of light parallel to the principal axis after refraction through a convex lens, it is observed that they meet at a point on the principal axis. Now, concave lens. Concave lens is thinner in the middle and thicker at the edges. In this case, the ray of light parallel to the principal axis after refraction get diverged and appear to come from a point on the principal axis on the same side of the lens. In the diagram, it is observed that the parallel light rays is coming from the left side and after refraction, they are coming out from a point on the principal axis. Refraction by spherical lenses. There are three rules for drawing the diagram by a concave lens as well as convex lens. The first rule is that in a convex lens, a ray of light parallel to the principal axis after refraction passes through the focus on the other side of the lens. In case of a concave lens, it appears to diverge from the focus on the same side of the lens, as shown in the diagram. Second rules. In a convex lens, a ray of light passing through the focus after refraction goes parallel to the principal axis. In case of a concave lens, a ray of light directed towards the focus after refraction goes parallel to the principal axis, as given in the diagram. Third rules. In a convex lens and concave lens, a ray of light passing through the optical center goes without any deviation, as given in the diagram. Image formed by convex lens. First one, when the object is at infinity, the image is formed at the focus f2. It is highly diminished, real, and inverted. In the given diagram, an object was placed at infinite distance from the convex lens, and the parallel ray of light is incident on the convex lens. After refraction, they are coincided at the point f2. Hence, the image is highly diminished. Next, when the object is beyond 2f1, then the image is formed between f2 and 2f2 as given in the diagram. Here, the object is placed beyond 2f1 and two rays from the top of that object are incident on the convex lens. After refraction, they coincided at a point where the image is formed on the principal axis. Here, the image is diminished, real, and inverted. Next, when the object is at 2f1, then two light rays are incident on the convex lens, and after refraction, they are coincided where the image is formed. The image is formed at 2f2. Here, the object size and image size are same. They're real and inverted. Next, when the object is present between f1 and 2f1, then in the same way two light rays will pass through the convex lens. One will be parallel to the principal axis, another through the optical center. After refraction, they coincided at a point beyond 2f2 where the image is formed. So the image is enlarged, real, and inverted. Next, when the object is at f1, then image will form at infinity, because after refraction the refracted ray will not coincide at any of the point. They are parallel to each other, that's why it is forming at infinity. So the image is highly enlarged, real, and inverted. Next, when the object is between f1 and O, means optical center, then it is observed that the refracted ray, they do not coincide, but if we'll extend the line backward, then they will coincide at a point where the image is formed. The image is formed beyond f1, it is enlarged, virtual, and erect. Only in this case the image is virtual and erect. Let's see the image formed by concave lens. First one, when the object is at infinity, then the image will be formed at focus f1 on the same side of the lens, and it is highly diminished, virtual, and erect. So in case of concave lens, it is observed that the image is virtual in the first one. Next, when the object is between infinity and f1, then the image will be formed between f1 and O on the same side of the lens. It is diminished, virtual, and erect, as shown in the diagram. Sign convention for the spherical lens. Here, the sign convention follow the Cartesian convention only. Already have done this process in case of mirror. Here in the same way, the object distance is always negative. Image distance can be positive or negative depending on the formation of image, whether it is real or virtual. For the real, it is positive, and for the virtual, it is negative. And the object height is always positive. Image height depends on the formation of image. If the image is formed downward, that is inverted, then it is negative, and if the image is formed upward, that is erect, then it is positive. Focal length of convex lens is positive, but focal length of concave lens is negative. Now the lens formula of the spherical lenses. It is observed that the relationship between object distance u, image distance v and focal length f can be expressed as 1 by v minus 1 by u equals to 1 by f. Magnification of the image produced by spherical lens. It is the ratio of the height of the image to the height of the object. Power of the lens is the reciprocal of the focal length. The SI unit of power is diopter, and it is defined as the power of lens whose focal length is 1 meter. The power of convex lens is positive and the power of concave lens is negative. We'll solve different numericals. Thank you everyone. Lens formula, home, magnification of the image and power of a lens in the next class.